All right, we got a lesson on circles today, and it's a lesson all about finding angle measures in a circle picture and segment lengths in a circle picture. There's two parts, kind of like the title says, finding angles, finding segments. So we're going to do angles on the front side of the paper, and segments we'll look at on the back. Now, this is kind of where circles get real. So you really got to pay close attention, and you may have to refer back to how I'm doing these problems at a later time, just to revisit it. Now, I also have my formula sheet handy here, because what I'm about to go through is actually on your formula sheet. It's this like big chunk in the middle here. There's two theorems. One's about angles, one's about segments. So what I've done is I've taken exactly what's on the formula sheet and I've copied it onto our notes. I mean, it's helpful that it's on your formula sheet, you guys, but it looks like a bunch of nonsense. So unless you can make sense of it, it's not going to help you on the exam. So this first theorem is all about finding angles in a circle picture. All right, so let's kind of make sense of it and figure out what it says. The theorem, which we could prove, it says the measure of an angle formed by two lines, and then they break it up into two different cases. So there's going to be two lines drawn in the picture, and the first case is when the lines intersect inside the circle. And they gave you a little diagram right here. So when your two lines meet inside the circle, so there's the point where they meet, the angle formed by the lines, which is angle 1 in my picture, the angle formed by the lines, and let's see, the lines intersect inside a circle, like we said, that angle is half the sum of the intercepted arcs. Okay, that's what it says on your formula sheet. So let's kind of like figure out what that means. Sum means add. We've seen intercepted arcs, we've seen that term in the last lesson, and here's what they mean by that. So if you look at the picture here, your lines are going to hit the circle in like 4 different places. If you connect between the two lines on this side of the circle, arc X, and if you connect between them on the other side of the circle, arc Y, those are the intercepted arcs. And they're telling me that angle 1 in the middle should be half of the sum of those two arcs. Okay, and we put the addition problem in parentheses because you have to do that first. You add the two arcs together and you take half of it. And that would be angle 1. That's the case when the lines meet inside the circle. If the lines meet outside the circle, which is all 3 of these scenarios right here. So notice your two lines, the point where they come together is the point that I just dotted, and angle 1 is the angle made between the lines. All of these are essentially the same thing. It's just what kind of lines they are. Like look at this third example. These are both tangent lines. The middle one is one tangent line and then another line, which we're going to name on the back side, another line that hits the circle twice, and then in the first case, both of these lines hit the circle twice. But it's all the same idea because the lines meet outside the circle. So when that's the case, the angle formed between the lines when they intersect outside the circle is half. That hasn't changed. Instead of it being half the sum, it's half the difference of the intercepted arcs. But same idea, so here's my two lines like on the first one. Your lines are going to intersect the circle. If you connect between them for the bigger arc, which is X, connect between them on the smaller part, XY. If you take the big arc minus the small one, the difference, half of that, you're going to have the angle where the lines meet. It's the same idea for the other two cases. So I do big arc minus small arc, half of that. Big arc minus small arc, half of that. All right, and like I said, this exact thing is on your formula sheet. So it's just a matter of you being able to use that. So let's try 3 examples. And on example 1 here, I can see that this is the first case. My 2 lines meet inside the circle. So I know I want to take half of the 2 arcs that are intercepted. So here's my 2 lines, and if it helps you to extend them, do that. If you connect between the lines on the left side of the circle and on the right side, those are the 2 intercepted arcs. So they kind of made it pretty easy for me. I know that angle X, the angle made between the lines, should be half of those 2 arcs added together. So all I'm going to do is plug that straight into my calculator. And angle X would be 68 degrees. For number 2, this is the case where the lines meet outside the circle. So I'm looking at this second little formula here. I got a tangent line and another one. So if I connect them here, 95 is the big arc. Connect them here, Z is the small arc. And notice they gave me the angle where the lines meet, angle 1. So I actually have that. I know the lines meet at an angle of 20. That should equal half of these 2 arcs subtracted. So I'm going to do 95 minus the small arc, which is Z. Now I have to solve this for Z. So can't just plug it into my calculator. You could divide by a half. You could distribute. I'm going to multiply by 2 because that's the opposite of dividing by a half. That'll cancel the half out. So then I'm looking at 40 equals 95 minus Z. And then if I subtract 95, I would have negative 55 equals negative Z. Keep going and divide by negative 1. Do not tell me that that arc is negative 55. That does not make sense. So obviously you're going to divide by negative 1, and it should be positive 55. Okay, so sometimes you might have to work backwards, like that example, but it's the same formula. Number 3 is where they're really testing your problem solving here. So it's the case again, case 2, where the lines meet outside the circle, and I'm given that angle. So I'm given the measure of angle 1 in the formula is 50. If I take the lines and I find the 2 arcs, see if I connect between the lines there, that's the big arc. Right there is the small arc. They didn't give me either of those. They told me the arc that I actually do not need. How nice of them. If this is 100, then I should be able to figure out that the rest of the circle is 260, right? Because I know there's 360 in a circle. So you got to be really smart here and use your algebra skills. When you don't know how big something is, you call it X. So I'm going to call this arc TW X because I don't know what it is. Then I need to call this other arc something in terms of X, so that way I'm not using more than one variable. I know that together they're 260, so this arc I can just call 260 minus X. Because say this is 50, then I know that the other arc has to be 210, because together they make 260. So this is you being like super smart with your algebra skills here. Here's how I'm going to set it up. The angle made between the lines is 50. So I have the angle 1 here. That should equal half of the big arc, 260 minus X, minus the smaller one, which I called X. Now I just have to solve this. So this would be 2X right here. X minus X, negative X minus X. That'd be minus 2X. Then I'm going to multiply by 2 to get rid of the half. And I've got 100 equals 260 minus 2X. Okay, I'm just going to plug it in my calculator from here because we all should be able to solve this. you would subtract 260, and then you'd divide by -2. Okay, so x equals 80, but is that my answer? I don't know, I gotta look. Again, don't screw up the sign and tell me it's -80. That does not make sense. You can't have a negative arc. Now, this arc would be 80 because that's x, but they actually want me to tell them the measure of arc TH, which is here, that minor arc. So let's see here, that's 260 minus x, which I know is 80, so that's 180 degrees. And shame on them, they should have used 3 letters to name that, but we'll let it slide. All right, so that's the theorem where you're finding angles. The second theorem, which is also on your formula sheet, is when you're finding missing segment lengths in a circle picture. Now, you guys should know that a tangent line touches a circle once. A secant line is what they call a line that intersects the circle twice. Just so you're smarter, now you know that. Over here, check it out, AB, that's a secant line. Hits the circle at 2 different places. You are all now much more intelligent because you know that. All right, so here it is. It's on the formula sheet. Again, it's super helpful, but it's also very confusing at the same time. So you've got to make sense of what it says. Let's read it and try to piece it together. So it says, for a given point and a circle, so same thing, you're going to have 2 lines drawn on your picture. They're either going to meet inside the circle or they're going to meet outside the circle. Okay, so kind of 3 different scenarios here. Now they say, okay, for these lines, the product, which I know means multiply, the product of the lengths of the 2 segments from the point to the circle. I'm going to highlight that. The lengths of the 2 segments from the point to the circle is constant. That just means is the same along any line through the point and circle. I don't know about you, but that kind of just sounds like a bunch of gibberish to me. It's a lot. So let me help you make sense of it. Like I said, there's 3 cases. The first case, the lines meet inside the circle. Very similar to the last one. Now, if that happens, you've got 2 lines here, and they kind of cut them off, and you're just looking at what they look like inside the circle. They're saying you can multiply the lengths of the 2 pieces on that line that are from the point to the circle. So here's what they mean. Like, here's one line. Point P is where the lines meet. That's the point they're talking about. Point P. Okay, so they're saying if you take from point P to the circle, that's C, and then from point P to the other side of the circle, that's D, you can multiply those pieces. And they did that right here with C times D. For the other segment, you can do the same thing. You can go from P to this side of the circle, which would be B long, and you can go from P to this side of the circle, which would be A long. You can multiply those 2 segments. And since these things are constant, you can set them equal. Okay, so do not make this case any more complicated than it needs to be. And I'm actually going to jump down here, and I'm going to do example 2 to kind of show you what they're saying. So this is a case where the lines meet inside the circle. Look at each line individually. So this line right here, basically, you guys, all they're telling you to do is multiply the 2 segments on that line. So this is 4.8, the other one's x. I can multiply those. And I can set that equal to the exact same idea for the other line. And those 2 pieces are both 7. So I'm just going to multiply those. Okay, well 7 times 7 I know is 49. And you should have 0 problems solving these once it's set up. So nearest tenth, that would be 10.2. Okay, so that's the case when the lines meet inside the circle. Realize there are proofs for these, and they're pretty intense. They all stem from similar triangles that we did last semester. So there is like a theory behind this madness here. That case is not that bad. It's the second two cases where the lines meet outside the circle that get a little complicated. Now, the reason they gave you two pictures is because case 2 is when they're both secant lines. They both hit the circle twice. Case 3, the bottom one's a secant line, but the other one's a tangent line. So that kind of changes things just a bit. But you guys, it's the same idea. If you go from the point where the lines meet to the circle, that piece is W. You can multiply that by the segment that's the point to the other side of the circle, which would be this whole thing, W plus X. Then they did the same thing for the other line, and they said, oh, from the point to the circle is Y, from the point to the other side of the circle is Y plus Z. And they set those equal. For the tangent line, the point to the circle is T, and then the point to the circle, that's the same segment, T again. So that's why they just wrote it T squared. You will always do that for a tangent line. And then the secant line looks very similar to what case 2 was. I want to make this a little bit less complicated for you. So can you draw a little side note here for these two cases? Here's how I think of it when I set up my equation. Okay, so I'm going to say there's two lines you're talking about. So line 1, I set that equal to line 2. Here's what I do. I take the piece outside the circle. So on this case, it'd be W is the piece outside the circle. And I multiply that by the entire segment length, which I would add those pieces together and say X plus W. And then I do the exact same setup for the second line. So personally, when I do these problems, it makes a lot more sense to me when I do the outside piece times the whole thing. Set that equal to the outside piece times the whole thing. So let me show you what I mean when I look at example 1 and example 3. So I know I'm going to use this outside total thing because the lines meet outside the circle. So I look at one line at a time. For the top line, I do the piece outside the circle, which is 6. And I set that equal to the total segment length, which would be 6 plus 8. I'd add them together. And then I do the same thing for the bottom line. So the piece outside the circle is 7, and I set that equal to the total length, which would be 7 plus Y. Once it's set up, it should not be that bad. So I'm going to distribute there and say that's 49 plus 7Y. And then I would just do 6 times 14 and say 84. Straight algebra from here, so let's see, I would subtract the 49 and divide by 7, and Y would equal 5. So the setup is obviously the challenging part. For example number 3, that's one where it had a tangent line, so I know there's going to be a t squared, or whatever variable it is. So here it is. I know it's always z squared because it's the point to the circle, which is z, and then the point to the circle again, so you'd multiply it by z, and it's always z squared. And then I do outside times total for the bottom line, so the outside piece is 8 times the entire thing, which is 8 plus 16. So let's just plug that right side into our calculators, and that's 192. And then I'm going to square root it because they want it to the nearest tenth. And that looks like 13.9.